Alright, so today we're starting on Chapter 8, which focuses on the concepts of expected value, standard deviation, and variance. So our learning targets for today are to understand the difference between mean and expected value and to calculate the expected value and variance. So hopefully the words mean and variance are familiar to you. We've studied both of those. The word that you probably haven't heard, or maybe you've heard but maybe didn't know what it meant, was expected value. So let's talk about how we sample in statistics really quickly, and that'll help you gain an understanding as to why we would use an expected value rather than a mean. So let's say we were going to do a study on like the types of food people most preferred, or something of this nature, right? And we have a huge sample of people, and we'll narrow this down to the United States just for ease, okay? And maybe we would even do it even smaller if we wanted to be more specific about our results, okay? Although there's other ways we could do that as well. Anyway, so, however we're going to do this, we could ask food chains for their records, what their sales were like. We could give a survey to people, though much less reliable. And basically what we'd want to do is we'd create a sample, and hopefully a random sample. Okay? And what a random sample means is that we're picking people at random so that we get an accurate view of what's happening across the United States. So if we're sampling people in the US, we're not just sampling people in Washington, we're sampling people hopefully from every state in urban, suburban, and rural centers, so that we have a good idea about the whole United States. We have a good picture, and our data is representative of the country. So in a random sample, let's say I'm going to sample 2,000 people, okay? I have 2,000 data points. I could calculate the mean, the standard deviation, the variance, as well as run a slew of other statistical tests and analyses and come up with some conclusion, right? Well, an expected value is different because whereas I have exactly 2,000 data points here, an expected value would suggest that we have an infinite number of data points, or data points that tend toward infinity in terms of their volume or their amount. So think of maybe somebody who is like that researcher I told you at Harvard who was interested in whether or not a quarter actually you had a 50% chance of tossing heads or tails, right? And he built that little coin flipping machine, right? And he was basically flipping the coin infinitely, right? For hours and hours without stopping, and he was getting results every time. It landed on heads, they would record it. Well, he didn't necessarily know how many trials he was going to do, but he was generating a percentage every time that coin flipped, right? Without knowing the exact total number of flips that was going to happen. And this is where an expected value comes in, okay? So before we explore that more thoroughly, we're going to review mean, because an expected value is a type of mean, but it's a mean of data points that tend toward infinity in their number. So as a quick review, if we calculate the mean, we basically sum all of our values together and divide by the number of values. So in this case, n equals 12. Okay, that's our number of data points. Summed up, also a quick review, when we know the number of data points we have, we use x bar to mean mean. So this says the mean equals, right, in this case, 11/4. Okay, so that's all the numbers added together and divided by 12. All right. Now, a little bit of algebraic manipulation. So basically, we could do what we just did again in a slightly different way. So we're going to take you back to the concept of grouping that this is hopefully how you learned how to multiply. We have two ones. The long way of doing it is to say 1 plus 1. Well, it's longer if you have more numbers. The shortcut way is multiplication. We have 2 1s, so we could say 2 times 1. Okay? And since we're finding a mean, we're going to be adding all the values together. We have 3 2's, or 3 groups of 2, so 3 times 2 is the same thing as saying 2 plus 2 times 2. Is this ringing a bell for you, hopefully? Okay, so I'm just going to finish this out with our little grouping method here. Okay, and this is, the fundamental basis of multiplication, right? This is why it works. All right, so basically what we did is we grouped these, and instead of adding each value, since they're not unique, right, there's some repetition, we just use multiplication to express them. All right, now I have each of these terms divided by 12. Okay, so I could also rewrite this as 2/12 times 1, right? Plus 3/12 times 2, right? Because 12 applies to each term, not just to the whole, it applies to the whole numerator, but each term in the numerator. I have 1/12 times 3 plus 4/12 times 4 plus 2/12 times 5. All right? So all of the things that we've done so far are the same. Now here's where expected value comes in. I could express 2/12 as a percentage, and that percent is about 16.6, okay? About, times 1, plus 25% times 2, plus 8.3% times 3, plus 33.3% times 4, times 4, that's a times, ooh. Okay, plus, again, 16.6% times 5. Okay, so here's the deal. If I were to say something like 75% of people 75% of people love Nutella. Okay, well, hopefully that number's closer to 100%, but there may be some naysayers. Okay, I don't know when I say 75% of people love Nutella if that 75% means 3 out of 4 people, or if it means 75 out of 100 people, or if it means 75,000 out of 100,000 people. It's a percentage, so I don't know the exact values. Well, this is where expected value comes in. When I say 16.6% of my data resulted in a 1, I don't really know how many data points I have, just that 16.6% yielded that result, right? This kind of helps me look at things toward infinity, because percentages don't have to necessarily be linked to a finite value, right? They can be dynamic and change, but it doesn't necessarily, we're not locked into having 12 in the denominator like we are with a finite sample, okay? So that brings us to expected value. So in math, when we say expected value, it means that we essentially have an expectation of an outcome. So the technical way of saying this is the expected outcome of an extremely long sequence, or sequence that tends toward infinity. This is what an expected value is. The idea is that it's not finite, okay? It goes on and on and on and on. And as a consequence, we can't just calculate a mean because we don't necessarily know how many data points we have. So in our mathematical definition, we would say the expectation of a random variable x is defined by, okay, this is how we notate. We say e of x, this means the expected value of x, or any variable, is equal to, do you all remember this from chapter 1, mu? This is a Greek letter that means mean, okay? And when we say that we're trying to find the mean, we're going to do exactly what we did on the other page. What we're going to say is it's the sum, that sigma means sum, of our x values, and we're saying x sub I because we have maybe a whole bunch of x values, right? And this little I just notates which one in the sequence we're talking about, times p sub I, and in this case, p sub I is the probability of each term in our sequence, okay? So all of these things mean the same. So if I say e of x, I'm really talking about mu, which means I'm really talking about the sum of all of our values. So as a quick reference, remember how we said 16.6% times 1 plus 25% times 2, and so on? Well, this 16.6% would be p sub 1, this would be p sub 2. The I just means the term number, kind of like what we did with the geometric and arithmetic sequences. All right, the x sub I would be this value, okay, the 1 and the 2. So it's the chance that you're going to get a 1, the chance that you're going to get a 2, right? Basically is what it's saying. So let's put this into practice. Okay, find the expected value. So we're going to say the expected value of x, because that's what variable we have, is 1 times 1's probability, which is 1/6, plus 2 times 2 probability, which is 1/6, and so on, right? All the way down. Okay, and this is an example of maybe, say, a six-faced or six-sided die, right? Because, oops, plus here, because six-sided die all have the same outcome probability, right? So when I add this together, I should get an expected value of 3.5. Now you might be thinking, why did we go to all that work when I knew the mean was going to be 3.5? Because this set of data it's symmetrical about 3.5, right? I've got the same number of probabilities below as above. Alright, well, yes, this is kind of a lame example in that way, but it was kind of to show you, using something you'd seen before, how this would work. Okay, now what happens if the probabilities are not the same? So again, I don't know my number of values, right? I just know that, you know, if I'm going to get a 1, I have a 0.4 chance of getting of a 1 occurring. I have a 0.25 chance of a 2 occurring, and so on. So let's try to find the expected value here, and what you're going to see is this is not symmetrical, so finding the midpoint, right, is not gonna work out for us, right? It's not gonna be 3. All right, so here we go. We say 1 times its probability plus our next x value, or in this case m value is 2 times its probability plus 3 times its probability, and so on until we've included all of our outcomes, possible outcomes, and associated probabilities. Okay, and this total of 1 is just basically making sure that our probabilities are valid. Because, well, if we don't add to 1, we can't really do any of this. So, okay, so I'm just putting this in my calculator and multiplying and adding where necessary, and I get a value of an expected value, or a mu, of 2.15. Okay. Alright, so that's my expected value based on these probabilities. Okay. Alright, so let's move on to variance. So I think the easiest way to remember what variance is to think of it as the distance from the mean. And I'm saying distance because how we calculate variance is similar to how we calculate distance using the distance formula. So variance is squared, and the reason we square is much like the distance formula, we can't have a negative variance because variance is a distance, right? So if you want to think of variance as the average squared distance from the mean, okay, alright, that's, I think, the best way to think of it. So when the variance of random variable x is defined by this, okay, so sigma, that's what this little Greek letter is, sigma squared is equal to the variance of x, which is equal to, okay, the sum of our x value again, except instead of just saying x sub I, it's x sub I quantity squared. Okay, so we're squaring that x value and we're timesing it by the probability. Then we're subtracting from that mu squared, or the mean, the expected value squared. The reason we're subtracting is because variance is the distance from the mean. Okay, pretty straightforward. And just as a reminder, the expected value of x is equal to the mu, right, which is equal to the sum of x sub I times p sub I. So what we just did, basically, this value here is what we just did squared, okay? And this is very similar to what we did, except instead of just saying x sub I times p sub I, we square this term. All right. And as a quick review, and I know you all know this, the standard deviation of a random variable is sigma. So the standard deviation is calculated by taking the square root of our variance.